meteor and how big it is and how massive it is, but we need to figure out what the proper scale-down mass is. So it already gives us those dimensionless quantities, and we have to figure out what to use. So first thing I like to do here, since all the variables they give us is kind of just laid out in the paragraph, I'd like to take like a little inventory of what we have, just for starters. So yeah, we broke it down to the meteor parameters, the crater parameters, and the constants. So those are all our variables. And then we just look to see what relationships we have between them. So I went through, mass is what we're trying to find. It gave us relationships between the modeled and meteor numbers for all of these, except the volume of the crater. So, and then for some of them, like the crater, the soil density, it doesn't actually tell us numbers, but it does tell us that in the model it's twice the density. So as long as we have some sort of relation, we can say that we have that. So that's our just little inventory. So now let's take a look at the dimensionless groups that we're given. So just keep that in mind. So we have the two densities, the density, mass, and volume, and then the more complicated one. So we have to kind of decide on which one to use, which one's going to be able to give us our mass. So that's what we kind of have in mind. And so let's look at this first one here. People like this one, not like this one. Thumbs down, thumbs up, let's do that. Okay, lots of thumbs down. Okay, so this one, correct, we don't like it. This does not have M in it, so it can't tell us any information. And as we see here, we actually already have information for the two rows. So remember, it's actually twice the density for both. So we can see that the dimensional quantities actually are equal if we compare them, because it's times 2 for both. So we can see it scales correctly, but that doesn't actually tell us anything new. So now let's look at this one. This one good, bad? But it has M in it.
But it has V too.
Ah, okay. So it has M, so that's kind of an initially good sign. However, as we see right here, we have to keep in mind we don't like V. We have no information for that. That can tell us nothing. We're essentially, solving an equation here. We're finding the equation. We have our one unknown. If we add another unknown, V, we can't solve it. So that one's thrown up too. Then we look at the last one. I hope this one works, because that's all we have left. Is this one good? People have success with this? Lots of thumbs up. Good. All right. So yeah, we check through. We have all of these. No sign of V. M's are only unknown. So we are happy. So then we can go on to actually solving it. So we know with dimensional analysis here, we need to set the two equal when we're doing for the model and when we're doing for the meteor. So just repeat it there. We use all the meteor parameters over there, model parameters here, and then we can first, before plugging in, why don't we solve for our one unknown? So our model mass is our one unknown. So do that. We're given the meteor mass. We're either given the values for these or the ratios. So that is something we can plug in here. And then it's just the algebra going through. So everyone get this number, something like this, 1.5 grams comes out to. Good amount of people? Yeah. So if you go through the math here, I think it's probably fairly common to make a math error if you tried to kind of do it at an earlier step. I would definitely recommend writing something out like this. So you can just plug all your values in at the end. So if we remember this, so I think it said this was like 100 meters wide, like very huge mass. But after all the scale down, it comes down to 1.5 grams, which, as Professor Duncan pointed out, is about the size of like a little BB, for just like what Ralphie wanted for Christmas. So that tiny little BB there is like the exact scale up for this giant meteor hitting. And that's just because of all these, the gravity is 500 times as much. All these things are scaled to make it a much more easily manageable test here. So, so yeah, that's the answer. But one thing also to kind of think about is what can this give you. So that tells you how to do the model. But let's just kind of take one little step further. So we didn't have V, but when we actually run this, throw that little BB down at like whatever we're using as our test soil here in this setup. If whatever we get for volume of the crater, we can scale up to what it would be like if that entire giant meteor actually came down and hit the Earth. So you do all those numbers out, and you get this giant factor right here. And so 10 to the 11th, the volume. So I just tried like 100 centimeter cube, so just like a small little kind of volume here. Throw that down, it's not going to displace that much soil. Then you multiply it by this factor, and you get this giant number. So just for reference, that would be like 4/10 of a kilometer cubed. So I don't know, that's probably around like a city block or something. So and then like that same amount high. So that's a very, very, very huge volume. So that's just kind of cool because in the lab scale you can actually scale it up and see what it would be like in real life. So, any questions on going through how we got the 1.5 dimensional analysis? Good? All right.